Thank you. We may need to look after this missing audiences first, right? Instead of finding. Thanks to the organizer, right? The Professor Lee Chang-wook and the professor, my goodness, his name is slipped away. Yeah, Professor Woo Jong-min from the Shanghai University, right? Yeah. Fudan University. I'm very sorry. Yeah, missing memory. And actually, it's always a great pleasure to meet some old friends and new friends here. So welcoming to the colleagues from the Shanghai, all the way up from Shanghai to Daejeon. I just wish you to have wonderful days in Daejeon and possibly also in Seoul. Okay. So today I'd like to talk about the recovery of missing samples in multi-channel oversampling. Think analog and direct digital. This is a simple motto of the signal processing field. Okay? And one of the central goals in signal processing is to reduce analog signal f of t, so some continuous time function as the engineers called it, into a digital signal f of t sub n at certain the sampling points t sub n, and then definitely we'd like to recover the original signal f of t from this discrete data f of t sub n, or in some cases some sample values of filtered signals of f of t, for example this derivative or Hilbert transform or some other things, right? Typically as the form of the series form of the summation of f of t sub n and some reconstruction functions which are independent of individual the input signal f of t, right? Then as this problem shows, this is a kind of the interpolation problem which should have infinitely many solutions unless we restrict the class of signals in a certain sense, right? So the fundamental questions in this field are what class of analog signals admit such a sampling series, and then how to take those sampling points t sub n and those reconstruct functions Sn of t. These two are the fundamental questions, but I'm not interested in this talk about these two, but okay. In the storage of the transmission of the signals can be, the digital signals can be contaminated in a certain way, or the part of this data can be missing. Okay? So what should we do in the case of there is some missing data, right? Definitely we have two options. The first option is to give it up, and that cannot be the topic of this talk. So the other option is to do something for the missing data, right? So how to recover those missing data. Okay? Actually, the early contributor in this field are usually people say the two people. One is the Professor KAIST. He is an electrical engineer. Among other things, he showed that to have a complete recovery of a signal, okay, one must sample at least twice times the bandwidth of a signal, which we now call as a KAIST rate. Okay? And another one is another guy is Claude Shannon, who is father of the information theory, and also he coined the very important, the indispensable word we are now using, the bit, right? Binary digit. Yeah, that was coined by him, right? He's responsible for the word, right? Okay. So a signal of finite energy, mathematically it means simply the L2 function. We say that such L2 function is band limited if it's Fourier transform, which I modify in this way, which I take the standardization, and it has the compact support. Okay. Then, by the celebrated Pallavina theorem, for any positive number b, if we are collecting all those L2 functions whose Fourier transform has a compact support in the closed interval from negative and b, that we denoted by the PWB, okay, Pallavina space. Then by the Pallavina theorem, right? Another characterization is this space is the same as collection of all those anti-analytic functions of the exponential type at most b, of which the restriction along the real line belongs to the L2R. Okay, so this is one another characterization. Then now we have classical celebrated Whittaker-Shannon Kotelnikov sampling theorem, which says that any signal from the Palomino space PWB can be reconstructed by its uniform sample values f of n pi over b tilde as a cardinal series, say the sum of the f of n pi over b tilde times, think of b tilde t over pi minus n, where the kernel function think of t, this is simply the sine pi t over pi t is the so-called cardinal sine function. Okay? Then just to look at this number, right? Pi over b tilde, this is a sampling period, so that it's reciprocal. B tilde over pi is a sampling rate. Okay? This is a rate how often we are choosing the sample values per unit of time. Okay? And in fact, the smallest possible the numbers for the b tilde is the number b. In that case, we call the b over pi is the Nyquist rate. Right? We cannot lower this number, because if we do it, if we choose b tilde less than b, then we are going to get so-called the aliasing error. Okay? So for complete reconstruction, okay, the number b tilde must be at least the equal to b, right, or bigger than this one. Okay? Recall that for any the input signal f of t from PWB and any number b tilde greater than or equal to b, okay, I claimed that it can be expanded into that fashion, right? So take the Fourier transform on both sides, then its Fourier transform will be given in these sequences, right? And note that, in fact, I'm assuming that f of t is coming PWB, and that means its Fourier transform has a compact support in a possibly smaller interval from negative b and b, right? So you can multiply both sides by the characteristic functions of the closed interval from negative b and b. Okay? If we do it, then left-hand side unchanged, and the right-hand side just simply changed into that fashion. Okay? Then take an inverse Fourier transform onto this series, then you are going to get another the sampling series expansion, which is quite similar to the original one, but it has some quite a remarkable difference, okay? As we can see right now. Okay? So now we have for any f coming from PWB and any b tilde which is strictly greater than b, we have two competing sampling series. One is of this one, and the other one is that one. Okay? They look quite similar, but certain differences we have, right? The first one is, in fact, is the orthonormal basis expansion in Hilbert space PWB tilde. Okay? This is an orthonormal basis expansion, and that means if we are losing any one of these coefficients, then okay, we have no way to recover the original signal by this formula. Okay? Because starting from the any basis, right, the expansion coefficient is uniquely determined by the input signal something. So any one of the missing, then we cannot recover the original one, right? But look at the second equation then. Okay? This is the so-called the oversampling expansion, or more precisely, this is a frame expansion in the Hilbert space PW pi. Whatever the frame is, I will introduce you the word frame a little bit shortly after. Okay? And this is a kind of the oversampling expansion. That means among this family of functions, right, they do not have a linear independence between those functions. Okay? For example, in the oversampling expansion with b tilde greater than, strictly greater than b, that means I'm in this one. Okay? Because both sides they converges uniformly over the global uniformly over the whole real line. Okay? Compute both sides at the same time, k pi over b tilde then. Okay? From the right hand side, you get this equation that you can divide it into two different parts. Okay? The one part is the same as this one, and the other part is the sum of all the k's which is not equal to k, right? Then look at this one, because b tilde is strictly greater than b over b tilde is less than 1. So, okay, subtract this quantity from both sides, then you are going to get this one. And this side has a non-zero coefficients, right? And that simply means we can solve f over k over b tilde from this equation, right? So, for example, if we are losing the case coefficient, then in this oversampling expansion, then it can be recovered from this equation very simply, right? So, and that means by the oversampling, we can recover any single, okay? In fact, any finite remaining missing samples, okay? By other known samples, f of n pi over b tilde when n is not equal to k, right? And even the oversampling, it can be used not just for the recovery, but it can also be used to reduce the noise sensitivity or to speed up the convergence rate of the sampling series, right? This is another advantage of, instead of the basis expansion, using the frame expansion, okay? This type of the classical, the Whittaker-Shannon-Kotelnikov sampling theorem has been extended to signals which are band limited in some generalized sense. For example, the collection of all those functions, right? Exponential type, entire analytic functions of exponential type at most sigma, of which the restriction of the real line belongs to the LP, that people call it by the Bernstein spaces, right? This is a temporal distribution, so that we can take its Fourier transform in a distribution sense. Then any member of this, any member in this spaces has a compactly supported the distribution whose support is confined on the closed interval from negative sigma to sigma, so that the signals from this space is band limited in some distribution sense. Okay? So this is quite a classic result, but in order to extend the sampling theorem, right, to signals which are possibly time limited, okay? And time limited means it cannot be band limited by the Heisenberg uncertainty principle. Okay? Then the classical theory cannot be applied to the time limited signals which are interesting enough. So in that case, we need the so-called concept of the shift invariant subspace of L to R, which are actually the building blocks of multi-resolution analysis or the wavelet theory. Okay? So as a preliminary, I'd like to introduce the shift invariant space in a short time. Okay? For starting from the any L2 functions, let V of phi to be a closed linear span of integer translation of that function phi. Okay? So that's the closed subspace of L to R, which we now call as a shift invariant space generated by this single generator phi of t, right? In that case, we say that those integer translation of phi is an orthonormal basis if it satisfies the so-called possible identity, right? For any the square sum over sequences, norm square of this is the same as the norm of this coefficient, right? Okay. If we weaken the condition a little bit, then we are going to get so-called the which basis of V of phi. Okay. It means that this family satisfies the norm square of this one is, in a sense, is equivalent to the norm of C below bounded by some positive numbers times norm square and the bounded above 2. In fact, rich basis is nothing but the orthomorphic image of any orthonormal basis, right? If we make the weaken the condition a little bit, then we are going to get the word frame. Okay? So it's a frame of the V of phi with frame bounds B and A if we satisfy this type of the inequality. Okay? And in those three cases, if this family is an orthonormal basis or a rich basis or a frame of V of phi, then we call this phi of t as an orthonormal generator or the rich generator or the frame generator, right? Okay. then we can see that phi of t minus n is an orthonormal basis of V of phi. This is the strongest condition. It implies a rich basis of V of phi, and which implies again this is the frame of V of phi. One of the most important role of the orthonormal basis is the expand some other the arbitrary vectors using this orthonormal basis, right? For the frame, even though the members of frame need not be linearly independent, but it can play quite a similar role in the following sense, right? Given any frame of the Hilbert spaces, they always exist a dual frame, okay, psi of t minus n, and it need not be the unique but, okay, by which we can expand any member from this Hilbert spaces into this so-called the frame expansion. Okay. If phi of t minus n is an orthonormal basis, then definitely this psi must coincide with phi. Okay. That's simply the orthonormal basis expansion we know already. Okay. And as I said, members of frame may not be linearly independent, right? Okay. May not be linearly independent, but this is not a disadvantage, but in a sense it can be the quite advantage we can have. So now let's get into the main result of this talk. So I'm starting with the continuous square integral function, which is a rich generator. And I'm going to assume that one technicality, the supremum of sum of this expression is finite. Okay? For example, any compactly supported continuous rich generator or any cardinal B-splines satisfy this condition. Okay? Then we can say that the shift invariant space generated by such generator, okay, actually the member of V of phi is in a symbol. This is a discrete continuous the convolution product. Okay, the coefficient is coming from all the square integrable sequences. The space is the members of this space is a continuous square integral functions. And furthermore, the space is a so-called reproducing kernel Hilbert space, because we don't need exactly the definition, so I'm not going to go into any details, but just one important thing is, if a certain sequence converges in this space, definitely in L2 sense, then automatically the sequence must converge absolutely and globally uniformly over the whole real line, right? That's a very nice condition we can expect from such a shift invariant space. Okay? Then we'd like to consider the following sampling expansion, right? For the arbitrary input signal from the V of phi, okay? This is our hope, right? We don't know unless there must be a certain other conditions, we don't know whether such the sampling series expansion is possible or not. Okay? There what I'm doing is we'd like to express the input signal f of t as a sum over j and the sum over n, Lj of f computed in a certain moment times the reconstruction function. Okay? Where the sigma j is a displacement coming from the real number, r is a certain positive integer, and those italic LJs are so-called the linear time invariant system. In other words, this is in engineering sense, this is a kind of the signal modulator. Okay? So if you are taking is given by the convolution operator with the impulse response L of t, and I'm assuming that those impulse response L of t is either translation of Dirac delta distribution or coming from the L1 functions or L2 functions or their linear combinations, right? Okay. So this means if we are taking the Fourier transform of both sides, then convolution becomes a product. So that means we are modifying the frequency of f, the input signal f, by multiplication of the impulse functions, the L of the Fourier transform of L, right? So that's the LTI system. Okay. So some modified signals. So we have n such modification. Using that and taking some sample values at a certain regularly spaced points, we'd like to recover the original signal. Okay. What's the condition for that? Okay. I set the Gj to be this sum, which is in fact called the Jacob transform of Lj of phi. Right? So, as a symbol denoted by Gj of C, and using this one, make capital N by small r matrix capital G of C, whose entries is given by G sub j and C plus k minus 1 times 2 pi over r. Okay? And I denote that alpha of G is the essential infimum of, this norm sign means the essential infimum, okay, of the smallest possible eigenvalue of positive semi-definite matrix G adjoint times G, right? And the beta of G to be, okay, the largest possible eigenvalues of positive semi-definite matrix G, the adjoint times G, and I'm taking its essential suprema, right? Then we can say, when can we expect such the sampling series expansion, right? It's given by the following condition, right? Assume that this essential infimum, essential supremum of the largest possible eigenvalue is finite. Okay? In fact, that is the equivalent to all those Jacob transformation is a 2 pi periodic and essentially bounded functions. Okay? Assume this condition, then we can expect such the series expansion where those family of reconstruction functions are they are forming the frame of V of phi if and only if alpha g is strictly away from 0. Okay? That's the necessary and sufficient condition. Moreover, in this case, okay, look at this number then. Okay? Lj of f sigma j plus n of r means that the number r is a sampling period for each modified signal, right? So its reciprocal 1 over r is a sampling the rate. Okay? Because we have n such channels, the total sampling rate must be equal to n, capital N over r. Okay? That must be greater than or equal to 1. That's one of the necessary conditions which we can get from this the necessary and sufficient conditions. Okay? Moreover, capital N is equal to R. That means the total sampling rate is equal to exactly 1, right? If and only if those reconstruction families, they are forming a rich basis of V of phi, right? So that means if these things happen, right? In other words, if we have the one total sampling rate, then we only have the rich basis expansion, and that means we cannot expect any recovering of any missing samples due to the uniqueness expansion of the basis expansion, right? So the game is over in that case. So we'd like to think about the case when, okay, this number is strictly greater than 1. Okay? So now I'm assume that sampling rate is strictly greater than 1. And I'm assuming those two numbers, right? The essential, the infimum, and the essential max supremum of the largest, smallest, and the largest eigenvalues is strictly away from 0 and bounded. And then by the proposition we have the overcomplete frame. Overcomplete means frame might have a chance to be a basis, right? But okay, in that case, it cannot be a basis at all. Really, we have some redundancy here. Okay? So we have overcomplete frame, say Sj of t minus nr, by which we can expand any input signal f from V of phi into this the oversampling expansion fashion, right? Now we are getting into the main concern, right? Now, when can it recover finitely or even infinitely many missing values among those sample values Lj of f sigma j plus nr? Okay? For simplicity, I'm assuming that we are missing samples only from a single channel. Okay? Then we may assume it to be it is coming from the first channel only, right? Just about the shuffling. Okay? So we write this the oversampling expansion. Okay, split the sum into two fashions. When j is equal to 1, right there, and when j is above 2, right, greater than or equal to 2. So some parts are missing from these sample values. Okay, from the first channeling. Okay. Okay. even though the theory can be extended to the case of the missing samples from several the channels too, right? But I will confine it to the missing samples are happening in a single channel. First, let's handle the finitely many missing samples. Assume that among those, the sample values from the first channel the signal, L1 of F, right? I'm assuming that these finitely many sample values are missing, right? Sigma 1 plus n k sub r, where n is moving from n sub 1 to n sub 2 and n sub m. So we have a totally little m missing samples. Okay? Then, let's set the A sub n to be the sequence, the Kronecker delta sequence minus L1 over S1 as sigma 1 plus nr. Then through the certain computations and boiling down the equations, then even though I'm not giving the details, but the equations can be boiled down into that fashion, right? It's simply becoming a Bx is equal to Z. The B is the infinitely by M matrices, X is the missing vectors, and the G is something known, so that we have overdetermined the system of equation for the M unknowns, which is represented by the vector capital X, right? Okay. So how to recover this missing vectors X? And the conditions we found is, assume that L1 over S1, the sequence L1 over S1 at the point sigma 1 plus N1 is one-sided supported, right? That means if there is the big positive number L, so that these numbers will vanish always for any number n less than or equal to L, or any number n which is greater than or equal to L. In that case, we call it as a one-sided supported. Then those missing samples can be recovered if and only if this sequence is not equal to the Kronecker delta sequences. Okay? That's the first condition, okay, that we can get. Now let's move to the infinitely many the samples that are missing. Okay? And before that, note that in this finitely many missing samples, the location of the missing data, okay, is occurring for the non-uniform times. Okay? So because I'm not assuming any condition on those the n sub something. Okay? So now we are considering the infinitely many missing samples, assuming that L1 over F sigma 1 plus mu times nr are missing, where the mu is certain the integers, okay, positive integers, and that means we have infinitely many missing samples, but the location of the missing sample are happening now at the regular points, okay, at the uniform points. And doing the similar things as before then, okay, we can set up the equations for the unknowns. Here's the X is equal to unknown vectors, which is of size of infinity by 1. Okay? And the coefficient matrix is given by that. This is again infinity by infinity matrices. And the G is another, the known, the infinity by 1 the vectors. Okay? So we can boil the problem down to solve that equation. Okay? Ax is equal to G, where the X is the unknown, the missings, and A is the infinity by infinity matrices. Okay? Then, okay, grouping the rows of A and G, mod the number mu. Okay? Then we can split this equation into mu equivalent equations, where I'm using the due coefficient matrix A alpha alpha and the G of alpha alpha. Okay? And so those the mu equations, A alpha x, that is equal to G alpha alpha. Okay? And see the patterns of those, the coefficients metric entries and the entries for the missing vectors, then actually we can read it out as a convolution equation. Okay? So using the entries, we can read it as A alpha convolution, x is equal to G the alpha alpha. Okay? Where which I mean the symbols A of alpha is equal to the sequence coming from the made of the A of alpha plus mu j. Okay? Then For any the square sum over sequence, let C had to be the so-called discrete Fourier transform of C, which is 2 pi periodic L2 functions. Okay? Then the necessary and sufficient condition for the possibility of recovering those infinitely many samples, if we have let me remind what the A sub alpha is. A sub alpha is given by this equation, okay? So for this sequence is now taking its discrete Fourier transformation, and if its essentially infimum is bounded away from 0 and is essentially bounded above, for some alphas where the possible indexes are coming from either from 0 or 1 and the mu minus 1, yeah, then the n can be recovered, though the infinitely many missing samples can be recovered exactly through that equation. Okay? Finally, to show just as a suggesting example, let's consider the following situation. Let phi 0 to be the characteristic function of the unit interval, that's the so-called hard scaling function, and the phi sub 2 to be the triple convolution product of phi 0. There is a cardinal B-splines of degree 2. Here are pictures for them. Okay? Then this generator, okay, is a compactly supported continuous rich generator, so that our technical hypothesis is satisfied. And the V of phi 2, the shift invariant space generated by phi t is nothing but the all differentiable L2 functions whose restriction on each the integer interval is a polynomial of degree n most 2, right? Then, okay, by the proposition I claim that any input signal from these spaces can be expanded into that fashion. Okay? Where the linear time invariant system, we are taking to make things as simple as identity, and those numbers sigma of j is 2/3 times j minus 1. And we can claim that those reconstruction functions S sub j are compactly supported functions whose graph is given below. Okay? And we can check the condition very easily. Right? For any j, this sequence is different from the Kronecker delta sequences, and it has a finite support. Okay? And that means any finitely many missing samples from any single channel can be recovered, right? Okay? How? For example, assuming that take a very simple signal from this one, okay? P2 plus P2 times t minus 3, is the expansion is given by that, where the red inked part, they are missing, right? Those 3 values are missing, okay? Then, actually starting from the overdetermined system of equation, okay? For finitely many unknowns, but we have infinitely many distinct equations, okay? After looking at those equations, we can find out some non-singular parts, okay? For example, it can be recovered by solving a linear system, okay? These coefficients are coming from the infinity by 3 matrix, which is the coefficient of the equation I mentioned before. So from this one, we can easily solve that equation. Okay? So this is just one of the illustrating example. Okay? Thank you for your attention.